let me finally also make an example for maybe the use of Arzela-Ascoli. I mean, it's beautiful, but the question is it also useful? I mean, equicontinuity might not be so clear. Is this a property which can easily be checked, or which is usually there in concrete situations? So let me look at an example. So namely consider, okay, so let us look on the unit ball. So in our continuous functions. So and consider a function thereof. Continuous function. So Fn should be a sequence of continuous functions which we assume to lie in a unit ball. So the norm is bounded. Okay, but so this is a situation we might have. We have a sequence of bounded continuous functions, and then of course we would like to work with them, and it's good to have an argument which tells us that we have a convergent subsequence. So I mean, that's what compactness gives us. Okay, but if we just have boundedness, if we are just in a unit ball, I mean, this is just too big. So we know we need this equicontinuity for this f. But so how can we ensure that the sequence of functions which we have has this equicontinuity property? Yeah, okay, and so if we just have a sequence of functions, of continuous functions in the unit ball, we don't have control whether they have to cluster or not. But what we need is also additional information about their derivatives. So if we can also control the derivatives of all the functions, then this gives us enough information that essentially they cannot be too far away from each other. So the question is, how can we ensure equicontinuity, let's say concretely, and this can be done, for example, if we have control over the derivatives. So assume that the functions are not only continuous but also differentiable, and so we assume that all the derivatives exist and that we also have control over the derivatives. So also the subnorm of the derivatives should be bounded. So this exists, and that there exists a bound, let's say a c bigger than 0, such that the norm of the derivative is less than c for all n. Yeah, and then this, I mean, having information about derivatives of functions gives quite a bit of properties estimating continuity or how close things are, and actually that's what we can do here. So namely, for equicontinuity, we have to check the continuity in a way which is independent of the index n. So we have to see that if we make x and y just close enough together, then this is as small as we want, and this should be independent of n, this argument. Yeah, okay. But now if we have differentiable functions, then by the mean value theorem, we can actually give quite precise estimates for the difference between the function at two arguments in terms of the derivative. So by the mean value theorem, this is the derivative of our function at some value between x and y, which I call xi, times x minus y. So that's the mean value theorem. And so you see, so maybe this here the mean value theorem, basic theorem for doing estimates of this kind in terms of the difference of the arguments and the derivative. Okay, and if we have enough knowledge about the derivative, namely if we know that it is bounded in a uniform way, independent of what the xi is, then really, I mean, we have here this derivative here can be estimated by c times x minus y. And now you see we have now lost the dependency on n in this estimate, and this tells us if I want to make this smaller than epsilon, okay, I just should choose x minus y smaller than epsilon divided by c. And this is independent of n. So this means, in this case, the sequence of functions is really equicontinuous. So this means Fn is not only a bounded sequence, but it's also equicontinuous. Okay, and then by what we have seen here. So we have it's equicontinuous and bounded, and that's the reason that it has a convergent subsequence. Okay, and the closeness, okay, we don't care about where the limit of this is. Okay, so I mean Fn is equicontinuous, and so by this and bounded, so we know we have this compactness, or we have the existence of a uniformly convergent subsequence. So if we want to have boundedness, really to use this theorem, we should take the closure of the set of the Fn's. So we should take also the closure of this, and I mean if a set is equicontinuous, then the closure is also equicontinuous. And then we have the closure of this set has all those properties, so it's compact, and this means that this sequence, which is a sequence in this set, has a uniform convergent subsequence. Okay, and that's a quite useful theorem, and it gives you also maybe a feeling for what this control in infinite dimensions means, or this equicontinuity. So it's not enough just to have the boundedness of your functions, because then this space is much too big. But if you can also control the derivatives of the functions, then this really means that that your sequence cannot be spread apart too much in this unit ball, but somehow they must still cluster somewhere. Okay, so I hope this gives you some idea that this theorem is not only very beautiful, but it can also be very useful in concrete applications. And Arzela-Ascoli is really a theorem which is used at many places, because having compactness arguments is very valuable and very useful. I mean, one is usually in need of compactness, because if you talk about arbitrary sequences, you cannot say much, and you need to start somewhere, and usually a good start is to know somehow that you have a convergent subsequence, and then you can use this subsequence for doing more. Maybe then you can show that the whole sequence converges or something like this, but at least you need a foot in the door. You have to start from somewhere. You need convergence of something. Okay, and compactness is exactly what gives you this convergence of is a subsequence, and in this setting of continuous functions, it's exactly Arzela-Ascoli which tells you what you need for getting this. Okay, so I think that's enough about this Arzela-Ascoli.